Welcome. In this video we're going to be doing more examples of proofs about functions on sets. So in the previous video we covered some proofs on functions and inverse images on sets. In this video we're going to be expanding on that and doing some more examples. So let's just rewind here and go back over what we did before. So in the previous video we proved the following. The theorem we proved was that we have some function that's going from some set A to B, and then we have a set E and F, which are both subsets of our range. And then we prove the following, that the some set operation, the inverse image on some set operation between E and F, and I'm going to put that as a star, is equal to the same set operation, the inverse image on the same set operation. And then put that as a star. Okay, where star in this case can be either union, intersection, or exclusion. Okay, with one proviso, I'm going to put a little asterisk there, and the asterisk means the asterisk in this point means if F is a subset of E, and that in this case only applies to the exclusion operator. Okay, so this theorem we proved, and we went over it in great detail in the previous video, and you should go back there if you want more insight into that. Okay, so in this video we're going to now examine. So this previous theorem was always examining inverse images. Now we're going to examine image sets. So now what we're going to do is say that our set E and F are subsets of our domain. Okay. So again, the picture we have in our head is we have A, some F, and we go here to some B range, right? And so in this theorem here, we had E and F to be sets in the range, and we were looking at what happens when we go back, what kind of sets are generated by the images or the inverse images of E and F. Now, in this one, we're going to do a similar thing, but we're going to say E and F now are kind of test sets, are going to be, that'll be my E and that'll be my F. That will be now in the domain. And we want to know what happens, what kind of behaviors, if we union these sets, we intersect them, or we exclude them from each other, what's going to happen over here? What can we say over here? All right, so let's now do that. So we're going to examine that. So we're going to actually write down the theorem straight away. So the theorem is, pretty straightforward. It's going to be very similar. So if you have F, A to B, and now if you have E and F are subsets of A, then the following statements are true. We can write that down as then. The following statements are true. That if I take the image of the union of E and F, it is equal to the union of the individual images. Okay, so this one behaves very similarly to the above case with inverse images. But here, when we go to intersection, it gets a little bit more complicated. If I write down now the intersection of two sets here, it is actually only a subset of the intersection of the images. Okay. And then finally, and this one's probably the most complex, if, and again we have this proviso that F in this particular case of C has to be a subset of E, otherwise it wouldn't make any sense, and we'll go over this in more detail later. Then the following is true, so we need this additional constraint to make this statement in E or C, that if I take the image set and I exclude the image set of F, this is a subset of the image of the exclusion in the domain. Okay, so in our video here, we're going to prove C. All right, so let's, in the next page, let's do that. All right, so we're going to prove C. So I'll write down what C is again. It's if F is some subset of E, and we have the following is true, then this is true. F of E, F of F, the exclusion, if we take the exclusion of the image of F away from the image of E, that is a subset of the image of the exclusion from the domain. Okay, so, right, let's see now, let's unwrap what we always do, our procedure. Is to kind of unwrap. We're going to unwrap the statement. So we want to unwrap the above statement here. We want to somehow turn this into something that's more concrete that we can use. So what we're going to say is then, first of all, we're talking about image sets. All right, so again, if I draw my little schematic, we have some X over here, some object that's in my domain, and I map it over via F. It goes here to Y, and that's the output. And so all of these above here, all of these are concerning objects Y in the range. All right, so we're taking sets over here, E and F. F is inside of E, and we're mapping it over. We want to know what happens to the Y's. What happens to the outputs over here? Okay, and where can we place them? Okay, so really we're talking about Y is equal to F of X. So we're talking about the images over in the Y domain. Okay, so let's now so X then is going to be some element then in E not F. Okay, that's the key object here. All right, that's the domain here. Okay, so let's now go through the proof. So so let's look at this statement then. So we have to do that. Our procedure then is to unwrap the above statement, and so we've done a little of the work from that. So what this means is, what we have to do is, for all Y, we want to prove that this set here is a subset of that subset, of this set. All right, so that, to unwrap that statement, we say that for all Y in this set here, I mean, this is an if-then statement. There's the then, and there's the if. Okay? And then, well, that's one if, all right? So this is the first if. And then there's a second statement here. We're unwrapping this statement here, which says that if Y is in this set here, then it's also in that set there. That's what we have to prove. So if for all Y in this set, it implies then that Y is also an element of E not F. F of E not F. Okay. Note that in this case, This is a one-directional implication. This is a one-directional implication, and this is different from previous video. In the previous video, we proved set equality, which required also proving the converse. We had to go backwards. But in this case, we're not going backwards. We're only proving that that this set is a subset of that. So it's a one-directional implication. So the proof is simpler. So the proof will be simpler. Okay. So now let's go into this and actually prove it. And in fact, it's not too hard to prove. In fact, we can just prove it right down here in this little space we have. Okay, so what we're going to do is make our proof. And I always like to start by, doing a proof colon, and that means we're really just starting in earnest. Okay, we've made some observations, but now we've unwrapped our statement to be a little bit more precise. So of course we pick y in f of E, exclude f of f. All right. Now I want to unwrap this statement even further. All right. This statement right here, if I put brackets around it, that statement is equivalent to saying that y is in the image of E, and that's important, that and y is not an element of f of f. By definition. Again, we're unwrapping this statement. We're simply rephrasing it. Okay? All right. So this so what does this imply? So then what does this imply? So always with these things, whenever we have these proofs involving functions, we state something about y, and then we have to go back and then say something about x. Okay, and that's the idea. Is the question then is question is what conditions does it put on x? That's really what we want to know. So what this implies then, what it implies then is x must be an element of E not F. Okay, and that must be true, that X must be an element of E not F. And we want to maybe go Y here a bit. It says, well, now we're going to do, we're going to say, well, if, for instance, X were an element of F, okay, that is, it's not inside this set, then that would imply that F of X equals Y would be an element of f of f. Okay, it would be in the range, which is not true. So we conclude then that, yeah, x must be an element of E not f, or E exclude f. Okay. This implies then, and from this we can conclude, now we go back. Now we want to say, okay, well, where do we place y? If we know where x is, now we can place y, we can go back. That implies then that y must be an element of f, the image of this set, right? Because if x is the point in the domain that generates y, and it's in this set, then that means the output, y, must be in the image of this set, E not f. Okay. All right, and that proves exactly the following, that because this is true for any y, we picked a y value, and that was arbitrary. That implies then that this is, in fact, a subset of this image. Okay. All right, and that will conclude our proof. But now I want to just go over, let's now just examine the proof. So first off, what we want to do is ask the question, why does F have to be a subset of E? And really the thing here is that it doesn't really have to be. But the condition makes the statement or the theorem non-trivial. Okay, so why is it non-trivial? So let's actually suppose that F is completely disjoint from E. All right, i.e., F is not a subset of E at all. In fact, it shares no points with it. Well, that would then imply then that that E not F would be just simply equal to E, because F doesn't exclude any points from E to begin with. Well, then let's write down our statement then. I'm saying that F of E exclude the image of F of F certainly would be true this statement would be trivial because, yes, if we take away points from the image from the original set, of course it's going to be smaller. Of course this is going to be true. That's true trivially. Okay, so now let's say, suppose, so if F shares no points with E, this statement is trivially true. Yes, if you take some image set and then you take away something, it's of course going to be less of a set. Okay, that makes sense because that's what we're doing here. That's what this operation does. It's just taking away points from F of E. Well, certainly that will be then a subset. Okay. Now it could if these points share nothing with it, it might not be a proper subset. It might actually be equal. But I'm not going to worry too much about those little details. Okay. So now suppose another thing. Now we're going to suppose that F intersect E is not equal to the null set. They do actually share some points in common, but F is still not a subset of E. Okay, right. So this is the example where F would be like this and E would be like that. So they do share some points in common, but they don't share all objects. Okay, so F is not a proper subset at all. Okay, all right. Well, now let's do this. So the thing to note here then is that let's look at the set. Now examine E not F. E not F then, of course, is actually just taking away these points right here, and these points, which were not part of F, not part of E to begin with, are sort of irrelevant. You're not taking them away from E, so that's going to be equal to E not F intersect E. Okay, and so you know, why not? So again, the only points we're taking away. So conclude the only objects we are, sorry for the handwriting there, are taking away are objects in E to begin with. In E to begin with. So objects that are outside of E are redundant. So all else is irrelevant. Okay, so and that's why we have this condition like that. So now I want to just give a quick example of why this subset is the way it is. So now we're going to take a function f of x is equal to y, and I'm going to make it equal to x squared. I'm going to say the domain now, and I'm going to just pick an arbitrary domain. It's going to be the closed interval from -2 to -2. Okay, I'm going to say now my range interval that I'm interested in. Oops. I'm going to back up here. Made a mistake. So obviously A is going to be the real line. That's my input set, and my output set B, well, that's going to be the semi-infinite, the positive reals, plus 0. Okay. So from this, what we want to do now is consider. We're going to consider E to be the closed interval -2 to 2. Now I'm going to consider a set F to being a subset of E, which is going to be the open interval 0 to 1. All right, so now we want to see how this works. So clearly, so you can note that, of course, F is in fact a proper subset of E. Okay, good. All right, and now let's examine. So again, what we're going to do here, our goal is to verify that f of E, not f of f, is in fact a subset of the image f of E, not f. Okay, so we want to verify this for this particular example, and it's pretty straightforward to do. So let's look at, so now let's look here. I want to look at E not F. So E not F, that's simply equal to, if we look at it, here's my interval, but I'm going to take out this little interval that's inside of it, and I end up with the following: -2 to 0. Okay, union 1 to 2. Okay, and that makes sense, right? We have this interval -2 to 2. And there's 0 in there, and we're taking out this bit right here. So we're going to have this interval here and that interval there remaining. Okay. All right. So now we want to know what's the image. So f of E not f is going to be, well, we can see the values that it ranges over. It ranges from -2 to 2, and if I plug that into x squared, we can clearly see that this has to equal, it goes all the way down to 0, and it goes all the way to -2, and it ranges up to 1 and 2, but we know whether it's positive or negative, the maximal value is 2, so we know what the image set is going to be 0 to 4 inclusive. Okay. All right, so now we want to check, what about the image f of E? Well, f of E, if you look at this, f of E is the entire set here. We know that's also equal to 4. But now let's look at f of f. This, of course, is equal to is equal to 0, 1, right? If I take 0, 1, if I take this open interval and I plug all those values into x squared, I'm going to get out essentially the same set. So now I want to, of course, if I exclude these points, then of course that f of E, if I take away then f of f, and that's going to be equal to, I'm going to just put it in more explicit form. I'm just plugging in here what that is, and taking away the open interval 0 to 1. That, of course, is equal to 1, 4. All right. So I'm examining this set, then I'm examining that set, and we can clearly see that that truly is a proper subset of f of the excluded domain. Okay, so what we can do there is, of course, say check, yeah, that does verify. This statement truly does verify for this example. So it does work out just as we thought. All right, so I hope this gives you some better ideas about how to prove things and how to make choices about how to start proofs, how to unwrap the statements involving proofs, and then make conclusions and then summarize. And of course, also see some good examples. All right, thank you very much.